This video is a brief description of kinetic energy, potential energy, and the conservation of the total energy. So let's consider a particle that is exposed to a net field force and is moving along a curve in space. And suppose that the particle is at P at T initial and Q at T final. Then the net work done on the particle as it moves from P to Q is given by this equation. So the work done is equal to the integration from P to Q of F dot R. And if we multiply by dt and divide by dt, we get F dot V dt, okay? And F is equal to M dV over dt. And so this gives this equation, which can be expressed as half M of integration of dV dot V. And it is equal to half m v final square minus half m v initial square. And this quantity is the energy associated with the motion of the particle, and it is known as the kinetic energy, okay? So if the particle has a mass m and speed v, then the kinetic energy is a scalar quantity equal to half mv square, okay? And so the total work done by the net force in displacing the particle is equal to the change in the kinetic energy of the particle. So similar to work, the SI unit of kinetic energy is the joule. So note here that the work energy theorem is applied only if the object is treated as a particle, so all of its parts are moving in exactly the same way. So as an example, consider a man standing on a skateboard on a horizontal surface. So if the man pushes the bar, then that would move him together with the skateboard backwards. And this motion is due to the reaction force exerted on him by this bar, okay? So the work done by each of the normal force and the weight is equal to 0 because each force is perpendicular to the displacement. So let's consider this point of application of the reaction force exerted by the bar on the man. So as you can see, this point did not move, and so the work done by this force is 0, and it follows from the work energy theorem that the man should not move, right? So the fact here is that it is incorrect to treat the man as a particle because different parts of his body move in different ways as he pushes the bar. And so the work energy theorem does not hold if we apply it to this point of application, okay, of the force. So the man should be treated as a system of particles, and we will see in a later video how the motion of a system of particles can be represented by the motion of its center of mass. So the center of mass behaves as if all of the mass of the object or system is concentrated there, and as if the net external force is applied there, okay? So in this case, the center of mass of the man plus the skateboard is moving, and the work energy theorem should be applied to this point, which is somewhere here. So the work energy theorem is an alternative method for describing motion without using Newton's laws. And it is especially useful in problems involving a varying force, okay? And as you can see, it contains only scalars, so it would be easier to use the Newton's laws, which has vectors. And also note here that both the work and the kinetic energy are not invariant quantities, so they have different values when measured in different inertial frames of reference. But from the principle of invariance, this equation, so the net work is equal to the change in kinetic energy, holds for any inertial frame. So as an example, let's consider a 6-kilogram block that is initially at rest, and then it is pushed to the right along a frictionless surface by a constant horizontal force of magnitude of 12 newtons, okay? And we want to find the block speed after it has moved a distance of 3 meters. So the net work done is equal to F dot S, which is equal to 12 times 3 cosine 0 equal to 36 joules. And this work is equal to the change in the kinetic energy of the block. So because it is initially at rest, the initial kinetic energy is 0. And from this, we get the final velocity as square root of 2 times work over mass, and is equal to 3.5 meter per second. So we will now consider the work done by a spring force. So suppose that we have a block that is attached to a light spring fixed at the other end on a frictionless horizontal surface. And suppose that an external force is applied to the block by either stretching it or compressing it through a small displacement, okay? So this displacement is measured from the equilibrium relaxed position x equals 0. And so in either case of stretching or compression, the spring will exert a restoring force Fs on the block that opposes the applied force and restores the block to its equilibrium position. And for many kinds of springs, and in the case of small displacements, the spring force varies linearly with the displacement of the block. So this equation is known as Hooke's law. So K here is a constant known as the force or spring constant, and it measures the stiffness of the spring. So the stiffer the spring, the larger is K, okay? And the minus sign here indicates that the spring force is always acting in a direction opposite to the displacement of the block. So the work done by the spring force in moving the block from an initial position x initial to x final is equal to the integration from x initial to final of fx dx, and if we substitute we get this equation, and if x initial is equal to x and x final is 0, then the work done by the spring force is equal to half kx squared. And as we shall see in the next slides, this quantity is the elastic potential energy stored in the spring. So now let's consider the work done by the gravitational force, which is in this case the weight, which is the gravitational force near the surface of the Earth. So suppose that a particle-like object of mass m is moving vertically upward or downward, okay? Near the surface of the Earth, where the gravitational acceleration is assumed to be constant. So if air resistance is neglected, then the only force that does work on the object is the gravitational force mg. So if we take the y-axis along the line of motion positive upwards and y equals 0 at the Earth's surface, then the work done by the gravitational force is equal to the integration of Fy dy, and Fy is constant, so we can put it out of the integral, and this gives the work done by the gravitational force is equal to mgy initial minus mgy final. And if y initial is equal to y and y final 0, we may write it as mgy, okay? So as you can see, if y final is greater than y initial, then the work done by the gravitational force on the object is negative. So if the object is moving upwards, the work done is negative, which means energy is taken away from the object, and that is why it would be slowing down, right? From work energy theorem. And if the object is falling, then y final is less than y initial, and the work done is positive, which means energy is transferred to the object. So the gravitational force is doing positive work on the object. So there are two kinds of forces, conservative and non-conservative. So a conservative force is a force that conserves the energy of a system when acting upon it. So the action of this force results in changing the kinetic energy of any object in the system, and this change will be stored in the system in the form of potential energy, okay? So for every conservative force, there is a certain potential energy associated with it. So as a result, the total energy of the system would not be dissipated, instead it would be conserved. So this is why it is known as a conservative force. And if the force does not act in this way, it is known as non-conservative. So properties of a conservative force is that the net work done by conservative force on a particle moving from one point to another is independent of the path taken by the particle, okay? So the work is independent of path. And an equivalent criteria is that the net work done by a conservative force in moving a particle through any closed path is equal to 0. So a force that does not meet these conditions is a non-conservative force, okay? So examples of conservative forces in mechanics are the gravitational and spring forces. So as we have seen here, the work depends only on the initial and final positions, okay? And so the work done by any of these forces is independent of the path taken by the object between the initial and final positions. And also if x initial is equal to x final or y initial is equal to y final, then the net work done by either the spring force or gravitational force is equal to 0. Which means that if the object takes a closed path, then the net work done is equal to 0 in each case, okay? So the force of friction is an example of a non-conservative force. And to understand this, let's consider this figure where there is a block sliding on a rough surface. And as you can see, there are two possible paths here between the initial and final positions. So the longer the path, the more interaction between the block and the surface, and the more the force of friction will act and do work on the block. And so this is why the force of friction is non-conservative, because the work depends on the path taken between the initial and final positions. So as mentioned previously, for every conservative force, there is a potential energy associated with it, okay? So for a system consisting of two or more objects, the potential energy U of the system is the energy associated with the configuration of the system. So the potential energy is the energy associated with the position of objects in the system relative to each other. So if the configuration of the system is changed, then the potential energy of that system will also change. So this kind of energy is defined only in terms of a conservative force, because if such a force acts on the system, then it will transform the kinetic energy of any object in the system into potential energy of the system as a whole, and vice versa, okay? And the name potential means that the system has potential to do work. So this kinetic energy, when transformed, is not dissipated, is not lost, but is conserved inside the system. So at a later time, this potential energy can be fully transformed back into kinetic energy, okay? So for a conservative force field, F, that is a function of x, y, and z, there always exists a scalar field U, or potential energy, that is related to F through this equation, okay? So F is equal to minus gradient of the potential energy. And also because the line integral of F is independent of the path joining the initial and final points, it follows that the curl of F is equal to 0, okay? And so the total work done by a conservative force moving a particle from P initial to P final is equal to this equation, and we substitute for F, and this gives a minus delta U. And so delta U is equal to minus the integral of F dot ds. So because only the change in the potential energy is significant, it follows that it does not matter where the reference point U initial is chosen, because if U initial is changed, then U final will also change, but delta U will remain constant. So please note that there is a typo here. It was y, but it is actually the unit vector j, okay? So let's consider now the gravitational and elastic potential energies. So as we have seen previously, the work done by the gravitational force in displacing a particle near the surface of the Earth from y initial to y final is given by this equation. And we know that because the gravitational force is conservative, then the work done is also equal to the change in the gravitational potential energy. And so we get this equation, and if we consider y final is equal to 0 and y initial is equal to y, then ug is equal to mgy. And from this we can find the gravitational force, which is equal to minus the differentiation of the potential energy with respect to y, because the motion here is only in one dimension, and we get minus mgj. So this is the gravitational potential energy of the object Earth system, okay? So as you can see, it depends on the configuration of the system. So it depends on the position of the object relative to the Earth. So for the elastic potential energy, we have seen that the work done by the spring force in moving an object from x initial to final is given by this equation. And from this we can find the change in the potential energy of the system, and if x initial is equal to x and x final is 0, then the elastic potential energy of the block spring system is equal to half kx squared. And from this we can find the spring force, which is minus the differentiation of u with respect to x, which is minus kxi. So let's now consider the conservation of mechanical energy. So the total mechanical energy of a system is defined as the sum of all of the kinetic energies of the objects within the system plus all of the potential energies of the system, okay? So let's consider an isolated system where there are no external forces acting on it, so the net external force is equal to 0. So the only forces acting in that case are internal forces, which may be conservative or non-conservative, okay? So if only internal conservative forces exist, then the work done by any of these forces on an object in the system will transform its kinetic energy into potential energy associated with that force, or vice versa. It is also possible that the internal conservative force will transform one form of potential energy into another, okay? So let's consider the work done by an internal conservative force on an object in the system. So it is equal to the change in the kinetic energy, and it is also equal to the minus change in the potential energy associated with that force, and so delta k is equal to minus delta u. So we may write this as k initial plus u initial is equal to k final plus u final. And if there is more than one internal conservative force, then there is a potential energy associated with each force, okay? So this is the total initial mechanical energy of the system, and this is the total final mechanical energy of the system. So E initial is equal to E final, and so delta E is equal to 0. So this shows that for an isolated system in which only conservative forces act, the total mechanical energy of the system remains constant, okay? So the change in the total mechanical energy is 0. So the figure here shows the changes in the energy of a ball that is thrown upwards. So at the position A, the total mechanical energy of the earth ball system is all kinetic. And then as the ball moves upwards, this kinetic energy gradually transforms into potential energy. So the potential energy will increase and the kinetic energy will decrease until it reaches 0 at the position C. And the potential energy here is maximum, so all of the kinetic energy is transformed into potential from A to C. And this potential energy at C is fully transformed again to kinetic energy as the ball moves from C to E. So as you can see throughout the motion, the total mechanical energy of the system, of the body Earth system, is conserved. So it does not change throughout the motion, okay? And so delta E is equal to 0. It is just that throughout the motion, the kinetic energy is transformed to potential and vice versa, but the total mechanical energy is constant. So this is the case when we have an isolated system and only internal conservative forces act. So suppose we have a system that is not isolated and we have internal and external conservative forces. So in that case, the change in the kinetic energy of the system is equal to the work done on the system by the internal conservative force, which is equal to minus delta U, plus the amount of kinetic energy changed due to the external conservative force, which is equal to minus delta U external, okay? And so this gives this equation. So this equation shows that the total mechanical energy of the system remains constant under both external and internal conservative forces. So in the case if there are external non-conservative forces acting on the system, or if there is heat transfer, or if the internal forces are non-conservative, then in all three cases the total mechanical energy may change and is no longer conserved. So let's consider this case. So the system is not isolated. There are internal conservative forces and there are also external non-conservative forces. So in this case, the change in the kinetic energy of the system is equal to the work done on the system by the internal conservative force, which is equal to minus delta U, plus the amount of kinetic energy changed due to an external non-conservative force, which is delta K external. So this equation shows that the total mechanical energy has changed by this amount, okay? So in general, the work done by a non-conservative force like friction cannot be calculated, but the change in the kinetic energy can be observed. And we will calculate this for the case of friction in the next slide. So in solving problems, you are free to choose the system. So suppose you have a block sliding on a surface and you choose the system as only the block, then friction will be an external non-conservative force, okay? And you apply this equation. But suppose you consider the system as both the block and the surface, then in that case, friction will be an internal non-conservative force and you apply this equation. So this is the change in the kinetic energy of the system due to an internal non-conservative force, okay? So now let's consider a system in which there are both internal and external conservative and non-conservative forces. And in this case, the change in the total mechanical energy of the system can be written in this form. So now let's consider friction, which is a non-conservative force. So if this force is applied externally to a system in which only internal conservative forces act, then it will decrease or dissipate the kinetic energy of the system by transforming it into thermal energy. So the work done by friction or any other non-conservative force cannot be calculated. So we cannot simply say that the work done by friction is the force of friction times displacement. And the reason behind this is that at a microscopic level, the frictional force is not a single force that acts at one point, but is a combination of forces acting at different points. But we still can calculate the loss in the kinetic energy of the object due to friction. So to do this, let's consider a block sliding on a rough surface, and let's consider the system as only the block, so friction will be external to the system. So we have, this is Newton's second law, so the minus force of friction is equal to ma, and using this kinematic equation and multiplying this by s, we get this relation. So this quantity here represents the magnitude of the loss in the kinetic energy of the block due to friction. And this loss of energy appears as thermal energy of the block and of the surface on which it slides. So let's consider now some examples of the conservation of energy. So for the first example, we have a roller coaster that starts from rest at A and we want to find its speed at C. So if we consider the system consisting of the roller coaster plus the track plus the earth, and if we ignore friction, then we may consider it as an isolated system where the only internal force acting is gravity, which is a conservative force, okay? And so we may apply this equation here for this situation. So the initial point is at A and the final at C. So at C there is kinetic and potential energy, and at A the kinetic energy is zero because the roller coaster started from rest, and there is potential energy, and from this we may find the speed of the roller coaster at C. So for the second example, we have two masses that are connected by a light rope that passes over a massless frictionless pulley, okay? And the system is released from rest at this position when M2 is above the ground by H, and we want to find the speed of M2 just before it hits the ground. So if we consider the system consisting of the two masses plus the pulley plus the earth, we may consider it as an isolated system where only gravity, which is an internal conservative force, is acting because we ignored friction, right? And so we may apply this equation. So at the initial position, there was only a potential energy of M2, and this was converted as the pulley is, this M2 is falling, it was converted to kinetic energy of M1, M2, and potential energy of M1. So from this equation, we may find the speed of M2 just before it hits the ground. And as you can see, because the two masses are connected by the rope, they have the same speed at any time, okay? So for this example here, we have a block that compresses a spring of negligible mass from its equilibrium position. So this is the initial position of the system, and then this block is free to move, so it is not attached to the spring, and once it is released, it can leave the spring and move, okay? So we want to find the speed of the block just as it leaves the spring. So if we consider the block plus the spring and the surface as the system, and if we neglect friction between the block and the surface, so the system may be considered as an isolated system where only the spring force acts internally. So the spring force is an internal conservative force. And so we may apply this equation. So this means for this system, energy is conserved, right? So at the initial position, there is only potential energy of the spring, and then there is no kinetic energy. And as the block, just as the block is leaving the spring, the potential energy is zero, and all of it is transformed into the kinetic energy of the block. So from this equation, we can find the speed of the block just as it leaves the spring. So it is equal to square root of k over mx, okay? So then the block will continue moving until it reaches the maximum height. So at the maximum height, the speed of the block is zero, which means its kinetic energy is zero. So between these two instances, the moment the block leaves the spring, and the instant it reached the maximum height, the kinetic energy, this kinetic energy here, because it's V initial here is the same as V final, so the kinetic energy is fully transformed to potential energy, okay? So the maximum height when there is no friction is equal to Vi square over 2G, okay? So now let's suppose that there is friction along this horizontal track. So in this case, we cannot apply this equation, but we have to apply this equation here because we considered the system consisting of the block, spring, and the surface. So the friction would be an internal non-conservative force. So if we want to find the maximum height, and let's suppose we take the initial position the moment the spring was still compressed, then we have the initial kinetic energy is 0. This is the initial potential energy. And the kinetic energy decrease of the block due to friction is equal to minus fkd. So d is the length of this track. And the final position, there is no kinetic energy, we have only potential energy. So from this equation, you may find now the maximum height reached in the case when there is friction along this horizontal track, okay? So the maximum height reached in the case when there is friction here is less than the maximum height when there is no friction, because part of the block's energy is dissipated through friction and converted to heat. So when there is a non-conservative force like friction, the kinetic energy, the initial kinetic energy, is not fully transformed into potential energy, but part of it is dissipated. So this example shows that the total mechanical energy of the system is not conserved when there is a non-conservative force acting on the system like friction. So let's now consider this example where there is an object that is released from rest at A and we want to find its speed at B, okay? So the track is considered frictionless, and if we suppose that the system consists of the object plus the track plus the earth, then we may consider it as an isolated system where the only internal force acting is gravity, which is conservative. And so we can apply the law of conservation of energy here, where the initial point is A and the final is at B, okay? So initially, all of the energy was potential energy and the speed of the object was 0, so it has 0 kinetic energy. Then as the object slides, its potential energy is transformed into kinetic energy. So it reaches maximum speed here, and then as it rises up again, part of this kinetic energy is transformed again into potential, okay? So at B, we have both kinetic and potential energy. So the potential is 2 mg r, okay, because the height from the Earth is 2r. So from this, we can find the speed of the object at B. So thank you for watching. Please don't forget to like and subscribe, and see you in the next video.